So now we're going to do a pair of problems that demonstrate two different points. You may have noticed that this region, a region that looked very much like this, appeared also in the area unit because regions having this shape actually tend to demonstrate a number of different points having to do with area and volume. So uh, what we're going to do is we're going to set up these two integrals. We're not going to solve them because, of course, the interesting part of these problems is really the setup more than actually just cranking through the algebra to find the value of the integral. So the first one is to set up an integral to find the volume of a solid whose base is the pink region and where the cross sections are perpendicular to the x-axis and where they are squares. So let's draw. I'll do this in blue. Okay. So actually, pick a slightly contrasting color. Sparkle. That's a good one. So our cross sections, that's not good. We'll switch back to blue. Okay, our cross sections are squares that have that length as the length of their side. So we know how to deal with that. What we know is that we can find this vertical distance between these two curves, which is just going to be the top curve minus the bottom curve. So let's write that here. Let's write 1 over x cubed plus 1 minus negative 1. That gives us the vertical distance, and we know that we want to square that. That gives us the area of a square that has that length of a side, and then we want to give it some thickness. We want to give it thickness in this direction, like that, and then we want to integrate it from the lowest possible x value to the highest possible x value. Well, the lowest possible x value is this 2, and the highest possible x value is this 3. So just to recap, this is the vertical distance. This is the area of a square whose side is that vertical distance. This is the volume of one slab. I haven't drawn the slab, but we've seen enough pictures of what the slab growing out of the page looks like. So this is the answer. This is the integral that gives the volume of the described solid. Okay, let's turn now to a slight variation on this problem. So let's set up an integral to find the volumes of the solid whose base is the same region, but where the cross sections are squares perpendicular to the line x equals 2. Okay, so first of all, we're looking for squares where one side of the square looks like that, or like this. So for one thing, since these squares are thick, their little bit of thickness is in the y direction. That means that we're going to have to end the integral with a dy, which means that we're going to have to put everything in terms of y. So the first thing that we need to do is do a quick calculation up here to solve for x in terms of y. I'll just zip through the algebra. Okay, so what we've seen is that we can write x as the cube root of 1 over y minus 1. That's the same curve as y equals 1 over x cubed plus 1. Okay, the next thing that we need to do is figure out what the length of the side of this square is. Now this is the tricky part. If you notice, the length of the side of the square is going to be the right curve minus the left curve, but what constitutes the right curve changes depending on how high up we are. In fact, I can put in this line right here, and what you can see is that when I'm below that red horizontal dotted line, the curve is the length of the side is given by the distance between the vertical line x equals 3 and x equals 2. In other words, it's just the horizontal distance of 1. But when I'm above the red dotted line, then right minus left, the horizontal distance here is given by the distance between this curve, x equals cube root of 1 over y minus 1, and the line x equals 2. So here, this is right, and this is left. But if I'm below the red horizontal line, now the vertical line x equals 3 becomes the right curve. The left curve doesn't change, but the right one does. So that means that I'm going to have to break this up into two integrals, which means that I need to know how high this point is, because I'm going to integrate in the y direction from negative 1 up to this point, and then from this point up to this point, using a different function depending on where I am. So let's do the bottom part. The bottom part is easy. So the bottom part, Let's write volume. It's going to equal the integral from -1, and I'll leave the top part of that blank for now. Let's just write the equation. Let's just write the expression for the area of a square. That's going to be 3 minus 2 squared, and we're integrating in the y direction, so that's dy. Now, what is this point here? Let's put a point. When I plug in x equals 3 into the original expression to get y, I get the point 3. 3 cubed is 27 and 1 is 28, so that's going to be 1 over 28. So this horizontal line is y equals 1 over 28. So that's what we have to integrate up to. And then we have to get up to this point in order to do the top. So let's add the integral in. I'll go over to this line. We're going to integrate from 1 over 28 up to here. This point is 2 comma. When I plug in 2 into the original equation, I get 1 over 2 cubed is 8 and 1 is 9, so that's 1/9. So I'm integrating up to y equals 1/9. And now I have to integrate right minus left and square it to get the area of the square. So that gives me cube root of 1 over y minus 1, that's the right curve, minus 2, that's the left curve, and I square it to get, this gives me the length of the side. I square it, I get the area of a square, and then I put dy after it. And that is the volume of this solid. So as you can see, sometimes you have to break this up into two integrals. This is a fairly difficult problem, but I'll tell you, it's actually one of my favorite problems. I like to give this a lot, so this is worth learning.